14 of November Daily Lead Code Challenge. And for guys in India, happy Children's Day. I'm not a child anymore, but, but it was always fun. We used to go to schools and we used to get chocolates on Children's Day. And okay, so I woke up early today and I've already solved this problem in the morning, and I regret not making a live video of it. Nevertheless, I'm going to write the code again and submit it again. So yeah, so the name of the problem is most stones removed with same row or column. So we have a 2D plane and we have n stones at some integer coordinate points, and each coordinate point may have at most one stone. So it can have one stone, or it may not have any stone. So a stone can be removed if it shares some other stone that has same column or same row, and we need to find the largest possible number of stones that can be removed. Okay, and for input we are given the coordinates of all the n stones, x and y, and we need to return the largest possible number of stones that can be removed. So let me open my I always forget the name of this application. Tayasui. I don't know. Okay. So here we are. So let's say we have a stone here, and a stone here, and a stone here, something like this. So these two stones they share the same row, and these two stones they share the same column, right? Now if I, let's say, remove this first, and then if I remove this second, then I can remove two stones, and I cannot remove this stone because this stone now does not have any other stone in its same in the same row or the same column. So but there can be a foolish way to do this. Let's say if I remove this stone first, now I cannot remove either of these stones because both of these stones now have nothing in common, neither the column or the row nor the row. So we should be careful of in the order we need to remove. But the more you think about it, you don't have to be really that careful, because there are really just two cases that can happen. One is when all the rows are in the same row. Let's say three cases. The case number two would be when all the stones are in the same column, or the third case is when there is a combination of stones which are in the same row or in the same column. So something like this. Yeah, something like this. The first row is simple because you can always keep one for the reference and remove all the stones, but you cannot remove the last one because you cannot remove that because now there are no stones in its row. Even for the second case, you can do this similarly. So if there are n rows in the same column, or n stones if there are n stones in the same row or n stones in the same column, you can remove n minus 1 stones, but you cannot remove the last stone. And things really get interesting when we have a case like this. In case such as these, in case such as this, so first you can eliminate it's like a blend of the above two cases. First you can get rid of all these columns, or you can start with rows as well, it does not matter. No, similarly, so you can first get rid of all these columns, because we have this, the main daddy here as a reference. So you can remove all the columns, all the branches, and then all we have is all we are left with is the first case. So apart from leaving one, you can remove all the other stones. So I want to say is we need to first group all the stones, that are in the same row or in the same column, into a group. So here what we had was a group, because we had a group here, because like these two have same row, so these two are connected, and these two have same column, these are connected, and then these two have same row, these are connected. So we can create a connected component out of these stones, and for each connected component of length n, we can remove at most n-1 stones, and that would be, my friend, I guess, the most optimal number removals, or the removals. The word optimal sounds a little foolish here, because it's just what we are doing here. And whenever it comes to finding connected components, you can either use DFS or my favorite data structure, union find. So that is something we're going to do. And if you don't know what union find is, I recommend you to go check it out, and I'll make a video on union find soon. But for now, I'm assuming, so you pause the video, go and check out what union find is, and come back. But for now, I'm assuming that everyone at this point knows what a union find is, and I'm a little lazier. So instead of writing the whole union find template, I already have some templates. Okay. What? Okay. I wrote a bash command, but I guess it refreshes whenever I close the terminal. That is gone. Okay, so I can open it again, not big deal. So desktops, documents, the coding interview, data structures. Okay. Come on. Yeah. So this is the union find template I have. I'll paste it in here. So yeah, this is the union find. I have class here, and then initialize with parent and size, and then I have these functions find. Oh, shit, I have this find function, and then I have this union function. So you can start using them. So I'm going to first create a UFO. That is what I call my union find objects. And I need to have some reference, right, in each row and each column. So I'm going to do that. I'm going to have a dictionary X and Y. So for each row and for each column, I'm going to have a daddy, a reference. Okay, and then for each stone in stones, now if the stone's X position is already having some reference. Okay, if stones of 0, so if the current stone's X position already has some other stone in the same row, then I'm going to union it with that reference. So I'm going to take that reference and union it with my current stones coordinates, and I'm using a tuple here instead of the list because list is immutable. Sorry, list is mutable, so it cannot be it is not hashable. And when it's unhashable, you cannot put it in dictionaries like this. So that's why I'm using a tuple. And if it has a reference in y, like if it has a column reference already, then I'm going to union this with that reference. And now I'm going to put the current stone as a reference to all other stones. So I'm just doing this. No, like I'm creating this as this will be a member of the group, so I can union my new stones with this stone to get into the group. Like this would be, this would be like your best friend, your girl bestie whom you use so that you can so that she can introduce, when you go out with your girl bestie, so that she can introduce you to her friends, so that then you can date them, something like that. It is, forget about it. Okay, so now we have formed all the groups, and now first we need to find the leaders of each group. So for stone in stones, s dot add find UFO dot find of stone. So now this will give me the group leaders of each and every connected components. So now I have the group leaders of each and every connected component in the set S. So now I can go to each of them. So for I in S, so in each group, if it contains n elements, I can remove n-1 stones. So answer plus is equals to UFO dot size of I minus 1, and I can return the answer. Okay, this should be a tuple. Where have I gone wrong? Okay. Wait. Now, where have I gone wrong? To have my union find. Okay. I should union Y reference. Such stupid. Such a stupid mistake. So guys, so yeah, that's it for today. I hope you have a great day ahead, and I'll make a video about union find soon. Yeah, see you tomorrow.